Hello, in this episode, we'll show an application of autoencoders to colorize a black and white photo image into a color picture. And we already mentioned it in the vision overview. Basically, we use an input of a black and white version of the image, put it in an autoencoder, so it replicates its own picture, but the target is a colored version. And what it will do is that it will turn this gray into this color, and if you give a new black and white photo, it will actually turn and try to attempt to color it. So how does that work out? So this is a code from a book called Advanced Deep Learning with TensorFlow 2.0, Keras, by Pack Publishing. And I'm taking an example from chapter 3 here. So let's see. So first to import the libraries, it's pretty much the standard TensorFlow libraries. We will use the CFAR10, which are basically all kind of objects of images, sample images. And then here is something that to convert a color picture, the data comes in a color picture, or we convert it to an RGB. So we just use this this algorithm to basically just fix the grayscale to 0.299 red plus 0.587 green plus 0.114 blue to make it a grayscale. Okay. So and then the first step is, of course, load the CFAR10 data. And we'll use the train and test data. It's an autoencoder, so we don't need a label. We just need the X data, the image data. And the image dimensions, we'll need to feed it to the autoencoder. So the image rows and columns and channels is here. Yeah, so we can save it. And here's an example of how the picture looks like. Some couple of the first 100 pictures of the CFAR data. So they are color picture originally. But we'll convert them into grayscale using the RGB to gray function we had before. And then the gray image will look like this. So the matching image. So what we'll do is that we put this in the autoencoder input, and the target will be this color version of it. Have the weights adjust so that we'll learn how to color on image, isn't it? We normalize the output to 255, meaning each pixel will range from 0 to 1 so that it's easier for the neural network to train, and also for the gray. And we reshape the image for this convolutional neural network, the row times columns times channel to feed it in there. Okay, so and there are a bunch of network parameters. Notably, the autoencoder goes from 256, 128 to 64, right? And here's the autoencoder model. First, we build the encoder. The encoder takes the input shape, right? The input shape is the rows, columns 28 by 28 by 1, okay? And then it goes into a two-dimensional convolutional layer with that shape. And convolutional layer, we already said that it's like a camera filter. It's a small pane of window that sweeps through the whole image and captures it. We'll have, as you can see here, the layer filters. The layer filters have 64, 128, 256. So it's a convolutional layer of this. And then for the latent vector, we have a latent dimension of 256. Okay, so we have that, and that's our encoder. Yeah. So here it's how it looks like: 32, 32, 1, 16, 16, 64, 8, 8, 128. And 4, 4, 26, and then here the latent vector 256. All right. And then the decoder is now it's expanding, and the expanding is a little tricky in convolutional layer, because in convolutional layer you can have a small pane sweeping through the large image and get a convolution out of it. But how do you get the opposite of it? That from a small size data, you expand it and blow it up. So you need something like this, what is called transpose convolution. What it does is that the convolutional layer basically goes through here and maps it and gets something. How do you go the reverse from this into this? So that's actually, there's an algebra done to it, and it can be done. And that function is basically called converse 2D transpose. So it's a transpose, it's an inverse of the convolution operation. So we do this to eventually get the original image, and that's our decoder, right? So you can see that from the latent vector, it eventually expands to 32 by 32 by 3 channel. Okay. The autoencoder is take the input, goes to the encoder, and then the decoder, and replicate itself. So the training, before the training, we set some parameters, reduce the learning rate, if the loss doesn't improve, and a whole bunch of things. But eventually we compiled the autoencoder with a mean square error loss and Adam optimizer. And here is the actual training autoencoder fit. At the X-train gray, you can see that we input the X-train of the gray version, grayscale version of it. And the target is X-train, which is the color version. And it takes about maybe 20 minutes to run this in a GPU. But eventually it can be run. I did it. And the test results you can predict by putting a test data. So it's an unseen data in the grayscale version. You put it in the autoencoder and the X decoded is the result. So if you plot it, you can see that you will see a color version. Okay. So this is a simple application of how to use an autoencoder to color a black and white grayscale image and how to convert it to a color picture. Thank you for watching this episode.